So as I mentioned before, we can classify many kinds of machine learning technique, right? So we can consider classification, regression, clustering, and demand generative reduction, and so on. So today I will shortly introduce about the support vector classifier, support vector machine for your filter. Even though you are familiar with this technique, but you should know about the mathematical part in detail. But even though it will take a long time for explain the all mathematical equations about the support vector machine, but I put the many equations as much as I can. So even though I shortly introduced the SVM in this time, but if you are interested in this technique, you can personally ask me, all right? So I can connect your research topic with the SVM personally if you are interested in this technique, okay? So SVM is very common and famous, but we should know why and how can we drive the SVM, the definition and the deep meaning from the margin and the support vector as well as the kernels concept. So when you look at this figure, there are two types of the data, the spam or non-spam, for example. So we want to classify two types of the data with the two lines. Which line is better for the classification? The number one, can have the margin with the red dot lines, and the line 2 can have the blue margin with the dot line. So heuristically, if we consider the classification as a person, maybe the line 2 is the better than line 1 because the location between two data type is the middle side of the line 2, right? So if you want to prove this, the answer with the computer, we can use the SVM, support vector machine, support vector classifier, all right? So using the margin concept, so if we maximize the margin with the SVM algorithm, the line 2, the number line 2 is the better than line 1 for the classification because the line 2 can have the maximum margin. I mean the blue lines, the distance. So the distance of the line 2 is the larger than line number 1. So naturally, we can conclude the line 2 is the better than line 1. Okay. So how can we get the maximum margin with the linear algebra mathematics part? The hyperplane concept is introduced for that. So hyperplane is the line for the classification of the two data type, for example. So we can put the equation, the W transpose inner product X plus B equal to 0. That is the general format of the hyperplane. So given the hyperplane, we can maximize the margin concept for the SVM. So in the given hyperplane equation, the W is the weight vector. So we can normalize the W to make constraint. So there are many kinds of dots in this figure. So which dot is the decision point for getting the maximum margin? We only consider the nearest point from the hyperplane first, and then we consider this constraint with the hyperplane equation for getting maximization of the margin. Okay, so when you check the left figure, so there are many kinds of the dots above side of this line, but xn is the closed point from this support vector, right? So we only consider the closest point for getting this problem. So we consider the distance between the closed point to the support vector, and we define this distance is the margin. Okay, so if we want to compute the distance to the hyperplane with the constraint, so this procedure is the normalization. If we abbreviate the procedures, so that is the normalization shortly. All right. So as I mentioned, that is the hyperplane, and we consider constraint with this equation. So if we want to maximize margin, we can consider this constraint about that. So maybe you know there are many the characteristics of the linear algebra mathematics. So with this the mathematic part, we can consider um, the maximum margin problem efficiently. So I will skip about the specific calculation in this page. So if you are interested in this part, you can personally ask me. I can complement it, okay? So if we want to compute the distance to hyperplane with the given constraint, naturally, we can utilize these equations. So finally, we can calculate the short answer about that. So this problem can be concluded with the max of this value for the maximization of the margin, and the constraint can be followed continuously. So we can consider all the points from the 1 to n. So that means we want to consider several points. So even though we changed several points about this constraint, but we want to consider the minimum length of the margin is just 1. So with this constraint, we consider this optimization problem through this mathematical part. Okay. And if we consider in detail about this optimization problem with the given the figure, this point is the most close location to the support vector line, right? But if we consider another point flexibly, we can we can change the first constraint equation to the general one. All right. So this means if this point x is the plus value, the y value can be 1. However, if we consider x4 point, that can be the minus. So the y can be the minus, the negative value too. So naturally, if we consider this procedure, the first given constraint can be changed to the general, the second constraint. So we generally can cover with this constraint about all that, regardless of the specific locations. So the first the optimization problem of the SVM generally changed to the general one, optimization problem form of the SVM. So the max of the 1 over the length of the W can be minimized the W transpose in a product W. All right. So 1 over 2 value can be continuously considered for the derivative concept. So I will skip about the proof of the mathematical part. And as I mentioned before, the constraint can be also generated with this form. So you are familiar with this optimization problem. So that can be a Lagrangian dual form, right? So if you are not familiar with these parts, maybe that can be the linear algebra and the optimization lecture. So maybe for the next semester or future, you can learn these technique in detail through the other lectures. Or if you are interested in these parts, you can personally ask me. All right. So anyway, you should be familiar with this form. The objective function and constraints pair can be one of the example of the optimization problem, regardless of the SVM or other techniques, all right? And if we consider the Lagrangian dual form, the objective function can be changed with this form. And with this form, if we minimize with respect to the W and V, we can satisfy the optimization problem form with the Lagrangian dual. And simultaneously, if we maximize with respect to the alpha, so alpha, if we maximize these parts with the alpha, naturally, the total value can be minimized, right? So the optimization problem of the SVM, minimize of the objective function can be satisfied simultaneously, all right? So I mean, if we want to optimize the given this form, for the efficiency, if we consider Lagrangian form, all right? So with the Lagrangian dual form, we can get the optimization problem efficiently, all right? So maybe this part can be the optimization lecture or the machine learning technique lecture. Maybe you can learn it in detail. So as I mentioned in a previous slide, Lagrangian dual can be composed of the objective function and the constraint optimization. So in a given a single equation, if we minimize some the features and maximize the backward part with the alpha, we can get the answer efficiently. So how can we consider the trade-off, the minimization and maximization parts of the constraints? In this part, we should consider deliberate part. So if we deliberate about W of the given equation, naturally we can delete the unnecessary part and we can reduce the value, right? And if we consider deliberate part about the B, naturally we can also delete with the unnecessary parts of the B, right? There is no B in this equation, so we can put this part is 0 right there, all right? So with the deliberate part concept, we can reduce the Lagrangian form to the simple, more simple one, right? So Finally, we can substitute into the Lagrangian form with this equation. So that is the objective function form, that is constraint. But as I mentioned before, with the many kinds of the mathematical equations, we can finally consider the the Lagrangian form. So the front part is the linear part, but the backward part is the quadratic, so not linear part, right? And the x value and the y value can be assumed with the given data set, right? So we don't know about the alpha in this example, in this equation. So if we want to maximize with respect to the alpha, subject to the alpha n equal to 0 or larger than 0. So finally, we can calculate with the quadratic programming concept. So if we consider the alpha value in the same given figure, finally, if we consider the closed point, the alpha n is larger than 0. But if the other points above the margin, the alpha n is just 0. So most the unnecessary point value of the alpha n is 0. So in SVM, many of the points, many of the alpha n of the points are 0 because of the mathematical and the quadratic programming. So we can prove these figures with the programming all by yourself if you are interested in. So finally, if we consider the support vector line with the maximization of the margin distance, as I mentioned, only the points on the support vector line can have the alpha n is the larger than 0, all right? So that is the mathematical part, but you should know it with my lecture shortly, all right? So that is the self-quiz, so you can refer this quiz for yourself, all right? So for example, for the SVM, we can maximize subject to the minimize this. So if you transform this to this one, we can minimize this form subject to the given constraint, right? And we can also maximize this SVM, the Lagrangian form subject to this given constraint. All right. But as I mentioned before, we should maximize the alpha, right? So this, the expression is not correct. All right. So I will upload my final PDF file iCampus. So if you're interested in SVM, you can refer it. But please refer this slide all by yourself only because of the copyright and my the future book. All right. So do not upload my file to the internet or public the site. Okay. So just to refer all by yourself. Okay. Thank you. So with the SVM, generally we can classify linearly. But if we have the high dimensional data, similar to the middle side of the figure, how can we classify these data sets? linearly. We cannot do it, right? So we should consider non-linearity of the SVM. So even though the original data set is a high-dimensional data set, but with the specific many kinds of the algorithms, we can transform to the high-dimensional reduction form, and finally we can classify these data to the third figures form. So for that, we should transform X space to the Z space. So data that are not linearly separable in the original X space may become linearly separable in Z space, much higher dimensional than X. So in this point, we should consider this form of the equation. So the front part is the linear form, but the middle and the backward part is the polynomial. So that can be higher dimensional, right? But if we replace the inner product of the X with the inner product of the Z on top of the transform technique, we can classify the complex data set, and as we check the equation on the screen, the remaining part cannot be affected with the transform part, right? With the quadratic programming. So QP is the abbreviation of the quadratic programming. So mathematically, we can get the answer of the classification, even though that is the high dimensional the equation. So we can't remain small even if the dimensionality of the Z space may be higher, larger with this form. So non-linear classification, right? And another way, we can use the many kinds of the kernel technique for the classification of the non-linear classification. So shortly, the backward part can be changed to the kernel trick form, such as the Gaussian kernel. So if we consider Gaussian kernel from the original data set to the one, we can reduce the complex parts of the mathematic equation. So finally, we can classify our complex data set with the Gaussian kernel. So what is the Gaussian kernel? If we consider 3 points in this figure, and the 2 points is very close. However, the other pair is the far, relatively, right? So if we consider Gaussian form with the given the 3 data points, the value of the closed, the similarity is just 1, right? So this value is 1. However, if we consider the similarity of the far distance to point pair, the similarity is 0 from the Gaussian distribution. So finally, this form of the backwards of the optimization problem can be 0 with the Gaussian kernel, and the similarity, the low similarity value of the 2 pairs can be just 1. So my point, regardless of the distance of the 2 pairs, we can simplify the backward form of the optimization problem to the 0 or 1 with the Gaussian kernel, right? So naturally, we can simplify the optimization problem, all right? So Conclusion of the SVM. SVM is generally used for the linear classification in a low-dimensional the data set, such as the spam or non-spam, or cancer or not cancer, and so on, right? But we should prove the mathematic equation. The support vector with the alpha is larger than 0 based on quadratic programming part. However, if you want to extend or if you want to consider nonlinear classification in SVM, we should consider transform technique or kernel algorithms in addition. All right? Okay. So within the limited time, I shortly introduce the SVM concept and some equations of the linear algebra. Maybe some of students were already familiar with the SVM, and a few students knew about this technique. So as I mentioned, linear SVM, the SVM can be SVC too, because the support vector machine, support vector classifier. All right. So the location of the linear SVC is there from the starting point. So you can't refer this slide all by yourself for your future too. Okay. Okay.